Okay, let's jump right in. When you're looking at the architecture of modern digital security, it's honestly so easy to get completely lost in the code. But in this explainer, we're doing something pretty fascinating. We're actually opening up a Gnosis repository to look at the absolute mathematical bedrock underneath all that code. And remember, Gnosis isn't just some tiny side project. It's a massive crypto ecosystem protecting real, tangible value. We're going to take these raw, unfiltered technical files and decode them, so you can see exactly how absolute security is built from the ground up. Now, this raw, kind of intimidating file path, this is our starting point. When you see a directory path like this, specifically hitting that fork race fold theorems directory, you aren't just looking at your everyday software code. You're literally looking at mathematical proofs of security. Because in the crypto world, just writing code that seems secure, yeah, that doesn't cut it. You need mathematical certainty. And this path right here represents the exact location where that certainty is forged. So we're going to unpack this specific directory, appropriately named lean_08 crypto, to see exactly how these four files mathematically verify cryptographic components. Think of this directory as a giant steel vault. Inside aren't just lines of standard programming, but rigorous, ironclad mathematical theorems that keep the entire Gnosis ecosystem locked down. Let's open up that vault and check out the four pillars holding up all this security. Here's our roadmap for today. First up, lean theorems in crypto. Second, defining cryptographic pseudo-randomness. Number 3, Klinemann-Seed indistinguishability. 4, playing PRG security games. And finally, number 5, playing PRF security games. Let's get to it. All right, Section 1, Lean Theorems in Crypto, the foundation. In this ecosystem, developers use Lean. Lean is a theorem prover, which means these files are absolute mathematical proofs, not just standard code. When developers write in Lean, they're rigorously proving that the system will follow exact mathematical laws with zero exceptions. This is the absolute bedrock of the security we're exploring. Moving on to Section 2, defining cryptographic pseudo-randomness, the illusion of randomness. This is our first vital component. The concept we're tackling here is this illusion of randomness, and it's absolutely crucial for any secure digital system. Because think about it, if an attacker can predict your numbers, well, your system is already broken. Take a look at our first file here, cryptographic pseudo-random.lean. Just by reading the name, you know exactly what they're going for. They're dedicating an entire mathematical theorem specifically to the concept of pseudo-randomness within a cryptographic context. To really grasp why that file is such a big deal, we need to unpack this definition. Pseudo-randomness is a process that appears perfectly random, but is actually generated by a deterministic mathematical algorithm. You see, computers are rule followers. They're entirely predictable, which means they can't easily generate true chaotic randomness. So they rely on this pseudo-randomness. But here is the real catch. This generated randomness has to be mathematically proven to be secure enough to trick an attacker. If it's deterministic, you literally have to prove the math is so incredibly complex that no human, or supercomputer for that matter, could ever predict it. Section 3, Klinemann-Seed indistinguishability, or what essentially acts as a digital blind taste test for hackers. This is where the abstract math of randomness meets the harsh reality of defending against an actual adversary. We're taking that pseudo-random math and putting it to the ultimate test. If we know the system uses a mathematical seed to generate security, a tiny little starting point of data that kicks off the whole pseudo-random process, the big question is, how do we mathematically prove a hacker can't guess it? It's nowhere near enough to just say, well, it's really hard to guess. Not in Lean. In Lean, we demand absolute proof. We have to demonstrate beyond a shadow of a doubt that guessing that seed is functionally impossible. And the answer to that? It lies right in this file. Klinemann-Seed indistinguishability.lean, it zeroes in on a very specific starting point, known as a Klinemann seed, and it introduces a massive, heavy-hitting word in cryptography, indistinguishability. Indistinguishability simply means an attacker cannot tell the difference between the system's generated output and actual true randomness. Imagine an attacker is wearing a blindfold, right? We hand them two streams of data. One is our Klinemann seed, and the other is pure chaotic random noise. If that attacker cannot reliably tell them apart, if it's basically a coin flip tie every single time they try to guess, then boom, the system is fundamentally secure. This file proves that this digital blind taste test will always end in a dead draw. All right, Section 4, playing PRG security games.
Cryptographers absolutely love framing security as an active battle between defender and attacker. It makes the math dynamic rather than just some static, boring equation. Check out the finiteindproggames.lean file. What this does is turn the abstract math of indistinguishability into a literal finite game played between the system and an adversary. By defining this as a finite game, the lean theorem creates a bounded environment. It's essentially setting up the rules of the board game, so we can definitively calculate the exact odds of the adversary ever winning. This particular game tests the PRG, or pseudo-random generator. Now, a PRG is an algorithm that takes that super short random seed we talked about earlier and expands it into a much longer sequence of pseudo-random numbers. It's kind of like taking a single drop of water and mathematically expanding it into an entire ocean of data. The game we're analyzing here tests the security of that exact expansion process. And this file maps out a precise step-by-step game. Step 1, the challenger generates a number. Now, it could be a genuinely real random number or a pseudo-random one generated by our PRG. Step 2, the adversary evaluates that number using absolutely whatever computational power they can get their hands on. And step 3, the adversary has to guess if the number is real or pseudo. The hacker is desperately trying to win by guessing correctly, and this file is right there to prove mathematically that they simply can't. Their odds are literally never better than a random coin flip. Which brings us to Section 5, playing PRF security games. Okay, so we've mastered generating numbers, but what about executing complex functions securely? A real cryptographic system relies on way more than just spitting out numbers. Now, you might notice this file, finite end PRF games, lean, looks incredibly similar to the last one. But look closely. The substitution of one single letter, swapping that G for an F, changes the whole cryptographic focus. We're shifting gears from a generator to a function. Enter the PRF, the pseudo-random function. Instead of just generating numbers, this bad boy tests functions. A PRF is a collection of functions that are completely indistinguishable from truly random functions to an attacker who doesn't have the secret key. So rather than just looking at the output data, the adversary is now trying to evaluate the behavior of the function itself. They're mapping inputs to outputs, frantically trying to find any sort of predictable pattern. Putting these two concepts side by side really shows you the absolute thoroughness of this whole repository. On the one hand, we've got finite-ind-prog games, testing those pseudo-random generators that expand seeds into numbers. And on the other, finite-ind-prif games, testing pseudo-random functions that evaluate inputs securely. Working together, these files prove that the Gnosis repository has complete, robust mathematical verification for both generating random numbers and executing secure cryptographic functions. They've literally covered both sides of the coin. So as we wrap up this explainer on the lean theorems inside this Gnosis codebase, I really want to leave you pondering this one thought. We've seen how developers use these incredible files to create totally unwinnable games for adversaries. We're forcing hackers into a digital blind taste test they can literally never figure out. So if security at this level is just a finite mathematical game, who is actually winning? Well, thanks to the sheer certainty of these mathematical proofs, the adversary mathematically cannot win. The unshakable foundation of victory is built right there into the code.